recording.
All right, so chapter 30, Law of Your Theories. Yeah, this one
Yeah,
is pretty dense.
yeah, we're probably gonna go way beyond 1 hour on this one. I would like to start by asking you, Marin, what did you understand this is about?
Uh, this is basically a way of encoding algebraic laws for a particular algebra in category theory, essentially.
I would go beyond your description, which is to go. There may be common algebraic aspects from objects within the same category, and what we want to do is to extract those patterns. That's what I understood from it. I don't know if it's correct or not.
All right. Uh, well, let's get started. Um, I like this first paragraph, so I'm going to read it. Um, Nowadays, you can't talk about functional programming without mentioning monads, but there is an alternative universe in which, by chance, Eugenio Moggi turned his attention to lower theories rather than monads. Let's explore that universe.
I don't know that
Uh,
author, so who's that one?
I think he was the first person who published a paper about using monads in programming.
Oh, is that the famous paper like people link it all the time?
Uh, Probably.
Okay.
Just, yeah, if you find that paper, check the author. It's probably this guy.
Yeah, there is a paper that I think it's way before like any sort of Haskell attempts at the monadic approach.
All right, so universal algebra. Um, there are many ways of describing algebras at various levels of abstraction. Yeah, we saw a couple of them already, right, in
Mm-hmm.
previous chapters. We tried to find a general language to describe things like monoids, groups, or rings. Groups and rings haven't been very relevant so far, but
Mm-hmm. Mm-hmm.
they are, yeah. And at the simplest level, all these constructions define operations on elements of a set, plus some laws that must be satisfied by these operations. For instance, a monoid can be defined in terms of a binary operation that is associative. And we also have a unit element and unit loss.
Mm-hmm.
Then it says we can turn the unit element into a nullary operation. That is, it takes no arguments and returns a special element of the set.
We've seen
Uh,
this before.
yeah, we've seen this before, and this is relevant because this allows us to talk about it in categorical terms, right? Because then the unit element becomes a morphism,
Mm-hmm. Mm-hmm.
which we need to do because we can't look inside of the object, right?
Mm-hmm.
Um, if we want to talk about groups, we add a unary operator that returns its inverse. Um, there are the left and right inverse laws. A ring defines two binary operations plus some other laws, and so on. Um, so big picture, an algebra is defined by a set of n-ary operations for various values of n and a set of equational identities. Um, Actually, this goes back to what is it? We're talking about algebra in one of the sessions. I don't remember which one.
I think it was chapter 24, F algebras or something.
And um, and you asked a question about um, what algebras are about, and you tentatively said they were about correctness, and I said no, they are about equality. Well, here we go. It's about equational identities.
Wait, I
So
don't I don't think well, I remember vaguely that conversation, but I think it was not. I think it was about something chapter of algebras. I don't know if it was specifically about algebras.
yeah, it's been a while, but yeah, it turns out the book does answer that question. But it's like, what
Well,
is it like?
six chapter later on.
I think that discussion was actually a little earlier than that, but anyways. Uh, Okay, so equation identities. These identities are all universally quantified. Um, Associativity must be satisfied for all possible combinations of three elements and so on. But incidentally, this eliminates fields from consideration because 0 has no inverse for multiplication,
Yeah, let's
which is
let's dive into that. What does this sentence mean? So are we saying that we cannot go after multiplying by 0, we cannot go back? That's what you're saying.
uh, that's not quite it. It's actually that the number 0, if you stick to, well, if you don't include any extensions to your number system,
Mm-hmm.
there's no inverse for 0, right? If you try to divide 1 by 0, that's like undefined, right?
Mm-hmm.
Which means that the inverse holds for every number except 0. So it's not actually universally quantified.
I don't think I understood what you said. That you said that the inverse holds for every number aside from 0, which means that if you pick a number and divide by another number
No, 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 not divide by another number. You take that number and divide 1 by it. That's the inverse.
in respect to multiplication.
Yes.
Oh, that makes sense. So that's what I asked. So if you multiply by 0, you cannot go back. But with the other numbers, you can.
Yeah, basically, yeah.
Okay.
Uh, so this definition can be extended to categories other than sets. If we replace the operations with morphisms,
Mm-hmm.
instead of a set, we select an object. Unary operation is just an endomorphism. And other arities are defined in terms of products, morphisms from products. And a general n-ary operation is a morphism from the nth power of A to A.
Yeah, yeah. So let's
And
get one thing straight. So we are basically anchoring the shit out of everything.
yeah, we are.
Okay.
Also, remember when we were using this exponential notation to define function types? No risk of
Yes.
confusion.
No, no, no. But here's the thing, though. This explanation of verity actually made that understanding of functions using exponential even more clear. Like, it's the problem is the following: the risk of confusion happens when you don't have that concept solidified. So then the notations need to be different because you're not used to interchange the notations because it makes sense. At this point in time, we've seen the exponential used so many times that for me it's already like the risk of confusion is low.
What I mean by that is that here you're saying that n is a number, but that's not really apparent from just this text, right? What if n is a general type? Then this becomes a function type instead of a product. You see the problem?
No, it's specifically saying that it's a number in the text
Well,
above.
well, in the text above, yes, but not here.
Oh, by itself. I
Yeah.
agree.
Uh, Anyways, we don't talk about function objects in this chapter, so that's probably fine.
Yeah, yeah.
Null-array operation is a morphism from the terminal object, the zeroth power of A, and so all we need in order to define any algebra is a category where the objects are powers of this special object A. And the specific algebra is encoded in the home sets of that category, and this is a Lover theory in a nutshell.
Okay, so stop right there. So we are establishing that the set of morphisms between objects which are powers of a special object A, this set of morphisms is the how do you pronounce it? Lauvire?
Lover.
Lauvire theory. So a Lauvire theory is basically a set of morphisms. Is that what you're saying?
Uh,
In which the objects about the morphisms are connecting objects that are powers of A.
Kinda. There's actually this roadmap here that makes it more clear, but
No, no,
yeah,
no.
it's basically.
Yeah, no, but we are this until now we are kind of establishing a first intuition. So like we're gonna go into the details, the nitty gritty right now, but it's important to have the first intuition there because we're gonna try to map the details to the first intuition. So am I correct in saying that I should imagine the Lawver theory being a set of morphisms between objects in which are powers of A?
You can probably think about it as being the category that includes those objects which are powers of A with the morphisms together.
Okay.
Um, all right, so here's the roadmap. We start with the category of finite sets, which is called finset, um,
Okay.
which is a funny name. It's skeleton F, which
Yeah,
we're
which is new nomenclature. Like we never seen what the heck is a skeleton, right?
yeah, this is going to be defined
Down there.
further ahead. Yeah.
Mhm.
The opposite category of F, which is F op, um, the law theory L is an object in the category law, um, and there's the model M for a law category, which is an object in this category here, which is also going to be defined below.
Yeah, and a model is basically the essence of something. That's what the way that he described it. So let's go through it.
All right, so here's a picture, which is going to get details.
Yeah,
So
okay, let's go read first because I have so many questions about this section, like 30.2, and this image. I have so many
okay,
questions.
okay.
Let's go through the text first. I'm gonna ask questions after we read it.
All right, so all Lawver theories share a common backbone. All objects in a Lawver theory are generated from just one object using products, really just powers. But how do we define these products in a general category? It turns out we can define the products using a mapping from a simpler category. Um, this simpler category may define coproducts instead of products, and we're going to use a contravariant functor to embed them in our target category, because it
Mhm.
turns coproducts into products and injections to projections.
Mhm.
So the choice for the backbone of the Lawver category is the category of finite sets. It contains the empty set, a singleton set 1, a two-element set 2, and so on. And objects in this category can be generated from the singleton set using coproducts. So, addition, essentially.
Mhm.
Um, Even though it's natural to think that there's only one empty set, there may be many distinct singleton sets because of,
They're not
well,
commutative, basically.
they are not associative either. Yeah,
Mhm.
but but even though, in particular, 1 plus 0 is different from 0 plus 1 and different from 1, even though they are all isomorphic.
Yeah, and that's
Because
the important part. That's the difference between thin sets and F. F will abstract out the thin sets isomorphic, well, equal members in quotes. They are equal up to isomorphism, so we're not going to count them as three. We're going to count all of them as one.
yeah, basically.
Yeah. Okay, let's continue because we are getting close to what I want to ask questions.
All right. Coproduct in category of sets is not associative, but we can fix that by building a category. Yeah, that's what you just said. Such a category is called a skeleton. In other words, the backbone of any Lawver theory is the skeleton F of finset. The objects in this category can be identified with natural numbers, including 0, that correspond to the element count in finset.
Yeah, so it doesn't matter if you're 0 plus 1 or 1 plus 0, it doesn't matter.
Yeah, in finset they are different, but in F they are not, because
Exactly.
it's
So
that.
F is just a bunch, is just, at first glance, is just a bunch of natural numbers. But the meaning behind those numbers is different than just counting. We are counting elements from thin set.
Yes, basically.
Okay.
Uh, Coproducts plays the role of addition. That's not new. Morphisms in F correspond to functions between finite sets.
That's where we start. I start having problems, because it says, for instance, there is a unique morphism from 0 to n. Which one? We have a set with no elements, and we have a set with n elements, right? So
Right.
what is the function that goes from 0 to n?
Well, it's the absurd function, basically.
It's the absurd function. Could you scroll up to the drawing and show me that? Are we talking about that arrow on the left of, yeah, going from
It's
0 to the 3?
yeah. There's this arrow for from 0 to 1. There's this arrow from 0 to 2. Like there's exactly one of them for each of them. But actually, those are all implementable using a single. Well, I'm going to say a single polymorphic function, but you can never call that function because, well, there are no elements here, right?
Yeah, no, I understand that, but I don't understand what function is that, because he says in the text as it would be a trivial or like an obvious fact. There's only one function from empty to n. Which one and why one? Only one.
Because it's the initial object of this category.
No, yes, it is the initial object of the category, but what is the function that goes from 0 to n? You said absurd.
Yeah, we saw that like way back. Let me just remember the page. It is 4063 in the PDF. I think it's like, what is it? Types and functions, examples of types. Uh, Here. Uh, this function.
Ah, okay, so you're talking about the function that you can never create, basically. You can never call this, I should say.
Yeah, yeah,
You can create one, of course. You can put absurd equal to undefined and put this type signature. But you can never call it because you cannot instantiate an element from void.
yes.
Okay, so that's one. Can you go back? I have more. There are more examples that I have more questions in after that one. Yeah,
All
go
right.
down, go down. Then it goes further and says
Yeah, I think
uh,
we are here.
no morphisms from n to empty. I guess it's because you cannot the same reason you cannot instantiate an element from empty. So no, you cannot go from anybody to it.
Uh, well, there are there are two answers to that question. The first answer is that, well, you can't really. Um, this appeals a little bit to constructive intuition or intuitionistic logic, I should say. There's like, yeah, if you could construct an arrow from some object to the void, then the object exists, so you can go to void, right? That's like a contradiction, essentially, in the logic.
Yeah, no, but I was kind of thinking on the implementation, like if I try to make that function in Haskell, a to void, I cannot do that because in the implementation on the body of the function, how can I put void in there?
You can only do that if you assume, like, if the parameters of the function are logically contradictory in some sense.
I don't follow. I still don't think how could you do what I just said?
Mm,
Like imagine function column arrow void. It doesn't matter what a is. You would never be able to construct that.
Uh, Actually, you can.
How?
Uh, well, I actually was looking at this earlier today, so
Um, so you made a function that goes from a to void. That's what you said?
um, from A to void. Actually, I'm not sure. Actually, if you can say for all A to void, that's
That's what the book said. There's no morphisms from n to empty.
except from void to void. Yeah.
Yeah, but no,
because
but that's
identities.
identity, right? So, well, anyway, I think we can go further, and then that it goes n morphisms from 1 to n. So my question is, we are going from the unit to n, to a.
From the unit to other numbers, basically.
Yeah. And why do we have n of those? Because you can always do it, I'm assuming.
You can always do it, but also, like for instance, there are two values in two, right?
Yes.
That's why it's called two.
Yes.
There's one value in one, that's why it's called one, right?
Yes. Yes.
If you're constructing a morphism that goes from one to two, you can choose uh, two possible implementations for that, basically, because inside of two there are two possible values.
Yeah, but that's not what the author said. The author said there's one morphism. There are n morphisms from 1 to n, right?
Yes,
But you just said that from, like, imagine that we're gonna have two morphisms from 1 to 2, basically,
yes,
which is
basically.
correct. One morphism from n to 1, because this is basically like a, uh,
Going to unit, basically.
yeah, you're collapsing. That's the verb. You're
Yeah,
collapsing all of the n objects to one, so there's only one
yes.
morphism. Okay, these help me because I was kind of getting confused. How do you know all of those things?
How do
Uh,
I know all of those things? Well,
no, not you, the author, because he's basically saying, for instance, blah 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 blah. And I was like, I maybe I'm stupid, but I'm not following why we have that quantity of morphisms for each case. But now it makes sense.
yeah, this goes all the way back to when we were talking about sums and products and the correspondence between those constructions and uh, integers, essentially. Well, not integers. Technically, they would be natural numbers, I guess.
Yeah, but let's go further. Here, n denotes an object in F corresponding to all n element sets in FinSet, which have been identified through isomorphisms. Well, we already know this, right? Because that's what F is. It's
Yes.
basically an abstraction on top of FinSet that removes the all of
Yeah,
the
it basically turns all of those isomorphisms into equalities,
exactly.
actually. Uh, okay, so using the category F, we can formally define a lower theory as a category L with a special functor going from the opposite category of F to L.
Okay, I have a question.
Okay,
So F is a category of products, right? F.
it's actually a category of sums.
Okay, so F opposite is a category of products.
It is a category of products, yes.
That means that means that we are going from a category of products, F opposite, and the functor goes to L, which is also a category of products. Right.
Yes,
Okay. That's a
it is
little
also.
weird, but okay.
Uh, all right. So this functor must be a bijection on objects, and it must preserve finite products. And that is, if you have I of L on a product, that's the same as of L on the left side and on the right side, and then you put those into a product.
Mm-hmm.
You may sometimes see this functor characterized as an identity on objects, which means that the objects in F and L are the same, and we
Well,
will therefore use the same names for them, denoting them by natural numbers.
but keep in mind that objects in F are not the same as sets, of course.
Yeah, because, well, we had to deal with the isomorphisms from FinSet, right?
Yeah, but let's go back to the that sentence. So the objects in F and L are the same. Do you have a
Yes.
problem with that? Because F is a bunch of sums. F opposite is a bunch of products. L is also a bunch of products. I think the objects must be the same.
Yeah, because um, like the opposite category, it flips out the morphisms, but it doesn't really Like it doesn't really change the objects theoretically, right?
Yeah, it doesn't change the objects, I think.
Yeah.
Okay,
The
but I
sums
have another
become
question though.
okay. Go
Do
ahead.
you see that between F opposite and L, after we go through the functor, you see that there are some proliferation of morphisms?
Yeah, those are the additional morphisms that encode the algebraic equalities that we're interested in.
Yeah, but I have a question. How are we mapping those though? Like, how is the
We
functor mapping that?
well, it isn't. It is introducing them actually.
Wait a moment though. So they're okay. So the category L has extra stuff that is not being
Yes.
mapped by in F opposite.
Yes.
Okay.
Uh, all right. So the home sets are in general richer than those in F opposites. They may contain morphisms other than the ones corresponding to functions in thin sets. The latter are sometimes called basic product operations. And the equational laws of a Lover theory are encoded in those morphisms, which is what we just said, basically. The key observation is that the singleton set
Wait a moment
1,
though.
okay,
We already established before that morphisms in thin set are basically n-ary functions, right?
yes,
So that means that by introducing extra ones in L, that means that we have extra operations that are only available after you go through the functor.
yes,
Okay. Okay, so basically the name of F is now being backbone makes sense because we are going from something basically like a boilerplate, and then the functor is what specializes the thing. Because you're
yeah,
going from
basically,
something generic, like something that can work for everything, and then after you go through IL, you basically have new operations that are exclusive to that theory.
yes.
Okay.
The key observation is that the singleton set 1 in F is mapped to the some object that we will also call 1 in L, and all other objects in L are automatically powers of this object. Yeah, this follows from the naturality conditions for the functors, right?
And all other objects in L are automatically powers of this object. Sure.
For instance, the two-element set 2 in F is the coproduct 1 plus 1, so it must be mapped to a product 1 times 1 or 1 squared in L. In this sense, the category F behaves like the logarithm of L, which is unusual, but okay. Um, among morphisms in L, we have those transferred by the functor IL from F, and they play a structural role. In particular, coproduct injections become product projections, P of K, P sub K, I should say. And a useful intuition is to imagine this projection as the prototype um, for a function of n variables that ignores all but the kth variable.
Wait a moment.
So,
So pk is a function that grabs product of n and it returns the kth one out of the product.
yeah, it basically takes a bunch of arguments, ignores everything except one of them, and returns that one.
Okay.
Um, conversely, constant morphisms from n to 1 in F become diagonal morphisms from 1 to n in L, and they
Yeah,
correspond to duplication of
yeah,
variables.
let's talk about that because I am still lost on this one. So a constant morphism from n to 1 in F means that we have a, a set of n members and you're going to unit. So you're
Yes,
collapsing.
yes,
Okay. It says that this represents diagonal morphisms, which I have no idea what it means, in L.
yes,
How and why?
because we're mapping from the opposite category of F, right? So the arrows are all flipped.
Mm-hmm.
which means you have a morphism going from 1 to 2, which previously was a morphism going from 2 to 1, to give a concrete example.
But why is that called diagonal though?
Because if you have one thing and you want to make a tuple of two things, the only thing you can do is copy that one thing.
I understand that, but I don't understand the naming still. Is that process called diagonal?
Normally, when you have like,
Oh, you mean the sense of diagonal of a matrix?
yeah, in that sense, yes.
Fuck. Okay, that should have been said, but okay. Uh,
Uh, that's not new terminology, by the way. They use the term diagonal to refer to profunctors a few chapters back as well.
yeah, but we're not talking about perfunctors here yet.
But the basic idea was the same. They were using diagonal elements to refer to profunctors that take and return the same type, right?
Yeah, but if you're gonna use the same terminology for two different things in two different contexts, we should explain that hey, this diagonal is not the same diagonal as that one necessarily. That just the base idea it is the same. Like the same no risk of confusion problem as always.
That's fair. Uh, the interesting morphisms in L are the ones that define the n-array operations other than projections. It's those morphisms that distinguish one law over theory from another.
Those are the extras.
Yes, those are the extras. They are the multiplications, additions, and selections of unit elements that define the algebra.
Okay.
To make L a full category, we also need compound operations from n to m, or equivalently using powers, right?
So you want to like a tuple of like I don't know 3 to go to a tuple of 2 or something.
Yeah, or something like that.
Okay.
Because of the simple structure of the category, they turn out to be products of simpler morphisms of the type n to 1. This is a generalization of the statement that a function that returns a product is a product of functions. Um, or as we've seen earlier, that the home functor is
Yeah, this
continuous.
is the same explanation of the exponential that we saw. Like products, they are actually just anchoring.
Uh,
Like instead of having a single function that returns a product, you can have multiple functions in the same. Like if you have a triplet, if you have a function that picks one element and returns a triplet, you actually have three functions in that sense.
yes, yes. Uh, Lover theory L based on F opposites.
Yeah, this is the
More.
same imagery that we have before, but um, oh, actually, let's just explore the right side because we already know F, we already know F op, we already know L. What the heck is M and set doing there?
Well, set, we've already seen. That's the set category, right?
Yes.
And M is a functor, which is the model of this particular theory. Well, a model of this particular theory. There can be more than one.
Yes. So, but we're gonna talk about that a little bit later, I guess.
We are, yes.
Okay.
Law theories form a category law, uh, great name by the way, in which morphisms are functors that preserve the finite products and commute with the functors I, this I here.
Mm-hmm.
Given two such theories, L and IL and L prime and IL prime, a morphism between them is a functor from L to L prime such that f of a product is the product of f of the components of the product, and f after IL is the same as just IL prime.
Wait a moment though. If you are commuting through two different theories, does that mean that we are kind of going from one algebra to another one?
Yes,
Oh. Okay, so in the category law, shit, we are basically using the functors as bridges to go from one universe to another universe of operations.
yes.
Okay, okay.
Yeah, and actually it says it right here. Morphisms between law-varied theories encapsulate the idea of interpretation of one theory inside another. For instance, group multiplication is monoid multiplication if we ignore the inverses.
That's crazy, crazy, man. Okay.
The simplest trivial example of a lower category is f-op itself, corresponding with the choice of the identity functor for IL. This lower theory has no operations or laws and happens to be the initial object in law.
Oh, but this is the identity functor then,
Yeah,
because we're just
like
going from one to itself.
if you say IL is the identity, then that gives you a trivial theory.
Yeah, that's basically FOP itself.
Yes.
That's not very interesting though.
Well, but it's an identity, so it's important.
No, it is an identity. Like it's basically like the simplest possible example, but that's not very useful in the sense of like I want to see something cool. I want to see something that was gonna blow my mind, and then you give me identity.
Well, it says it's almost like the book reads your mind, right? It would be very helpful to present a non-trivial example, but it would be hard to explain it without first understanding what models are. So models.
Yeah, this is the last part of the diagram.
Yeah, the M functor, basically. Uh, the key to understand Lover theories is to realize that one such theory generalizes a lot of individual algebras that share the same structure. For instance, the Lover theory of monoids describes the essence of being a monoid. It must be valid for all monoids. A particular monoid becomes a model of such a theory. And a model is defined as a functor from the Lover theory L to the category of sets set. Um, there are generalizations that use other categories than set, but yeah, we're not talking about them in this book. Since the structure of L depends on products, we require that such a functor preserve finite products. So no messing about with those. And a model of L, also called the algebra over the Lover theory L, is therefore defined by a functor. And here it is.
Okay, so if let me see if I understand. The model is L or M?
The model is M.
Okay. So M is a functor, and that's a model.
It's a model because it takes a Lover theory as its starting point.
Yeah, sure. This is okay.
Notice that we require the preservation of products only up to isomorphism, of course. Um,
Of course.
Preservation of products by models means that the image of M in set is a sequence of sets generated by powers of the set M1, which is the image of the object 1 from L. Let's call this set A.
Wait a moment though.
Uh, okay.
So it's a sequence of sets generated by the powers of the set M1, which means that we are grabbing the natural number 1, which in L represents a tuple of one element,
Yes.
that in F is basically all the possible combinations of a singleton set,
Yes.
and we are passing that through that class, let's say, one, and passing that through M. We're gonna get something on the side of sets, and that is a
Yes.
sequence of generated sets.
Well, the sets that you get after passing 1 through M is A, actually.
Okay, and then we are gonna use powers of A, and those will be the elements inside the generated sets.
Yeah, the powers of A are they are the image of M, basically.
Okay. Okay,
Like
okay,
they are
okay.
the objects that M can possibly return, so to speak.
Okay.
This set is sometimes called a sort, and such an algebra is called single-sorted. There are generalizations into multi-sorted algebras, but we actually don't talk about this in the book. Um, in particular, binary operations are mapped to functions from A and A to A. And as with any functor, it's possible that multiple morphisms in L are
Wait,
collapsed to the same function in set.
in L, that function that we are looking at right now, this is a 2 to 1. Then a 1
Yeah,
2 to the power 1 to the power of 2 to the 1 of power of 1.
yeah, in L that would be the case, yes.
Okay. Okay.
Incidentally, the fact that all laws are universally quantified equalities means that every law over theory has a trivial model, a constant functor, mapping all objects to the singleton set and all morphisms to the identity function on it, which is not very interesting, to be honest.
Yes.
um, a general morphism in L of the form m to n is mapped to a function, this,
Not surprisingly.
not surprisingly. If we have two different models, a natural transformation between them is a family of functions indexed by n. So this, or equivalently this, where b is n1. Uh,
Uh, Wait. B is n1. So we are putting that to the power of n.
which is the
Uh,
number that's indexing
that's a
the
transformation.
natural transformation, yes.
Okay, actually this is fine because m is a in this case. Well, a is equal to m1.
Yes.
Okay.
Uh, the naturality condition guarantees the preservation of n-ary operations, so this equality holds, where f from n to 1 is an n-ary operation in L.
Yes.
So n of f after mu of n is the same as mu of 1 after m of f. The functors that define models form a category of models, which is the thing that we saw earlier, mod L set, with natural transformations as morphisms.
Yeah, but I'm having a hard time giving an intuition of what the heck is a model. Because in the beginning of this section he said it's what's capturing the essence of something. Where is the essence being captured here?
Well, it's being projected onto the category set, um, and then depending on the specific model, you may be interested in different properties of the theory, I guess. And so, depending on the exact image of M in set, uh, you get to see a different aspect of your theory, basically.
Okay, so you're basically saying that the projection of the theory on set is going to give you more insight, maybe.
Yes.
Okay.
Yeah, and don't forget there may be, well, because we're talking about natural transformations, obviously there may be multiple models, right?
Yeah, yeah, but I don't. That's another question that I have. What in terms of intuition the natural transformations are doing here? Like we have the same theory L, and we are going to set in two different ways, using M and using N. Having an operation that which is a natural transformation that goes between the two, what does that mean?
Uh, well, you are mapping the objects that are the image of M to objects that are the image of N in this case. And the mapping is indexed by the number of elements in the product, right? Because all the elements from the source category L are products, right?
No, yeah, I understand what you're saying, but I don't know what it means.
You are basically translating products of elements from one algebraic, well, from the same algebraic theory, the same Liouville theory, to different representations, basically.
Wait, repeat what you said at the end there.
Like, basically, you have two different ways to represent your Liouville theory in terms of sets, and you're just going from one to the other.
Wait, so are you saying that the models are basically the implementation of a theory?
Not quite, because the laws of the theory are in L, actually.
No, but that's the thing. Do you know the notational semantics, right?
A little bit, yes.
So I'm kind of trying to use that interpretation. It's basically like L, in the way that you said it, it reminded me that, well, it gave me the correspondent thought process, and I don't know if this makes sense. L is the notational part, is the abstract, is where the semantics live, where the definition of semantics live. And set may be the way that you're going to implement those semantics, and you can have multiple ways of implementing the same semantics. Hence, why more than one model? And a natural transformation between the two in this interpretation would mean you can go from one implementation to the other.
Uh,
Again, I don't know if this makes sense, but the way that you said it reminded me of that.
it kind of does. You can think about it that you can. Well, I'm going to pull compilers into this because why not? You can think of L as being like uh, an abstract model, and then you can think of M as being uh, a concrete implementation of the abstract
Yeah,
model.
exactly.
And then you can think of the natural transformation between two such models as a compiler from one to the other or something.
Yes, exactly. Yeah, we basically said the same idea with different terminology. Okay, I liked it. I liked it.
Where was I?
Consider no no no. Consider a model from the trivial. That's where you were.
All right, thanks. Yeah, consider that model for the trivial category f-op. Such a model is completely determined by its value at 1, m1. Since m1 can be any set, there are as many of these models as there are sets in set. And moreover, every morphism in mod from f of op to set, a natural transformation between functors m and n, is uniquely determined by its components at m1.
Wait a moment.
And okay.
What? How do we know that mod of FOP set is a natural transformation between functors m and n?
This is actually the category of natural transformations between models from f of op to set.
Okay, so the morphisms in this category is way above, well, way above only m and m. There are many ones in there, potentially.
Yeah, this is a category of models for this particular Lawver theory, basically.
Okay, so two out of the possible many morphisms in this category is actually not true. One of the morphisms of this category is the natural transformation between m and m.
Yeah.
Okay.
Uh, okay, every morphism, blah blah blah, is uniquely identified by its component at m1.
Mm-hmm.
And conversely, every function uh, from m1 to n1 induces a natural transformation between the two models m and n, and
Makes sense.
therefore this category is equivalent to set.
Yeah, that last part is kind of crazy. So what we are saying is that, oh, it's because it's a one-to-one mapping, essentially.
Yeah, and it has to be a one-to-one mapping because we're taking f of op, which has no interesting morphisms.
Okay. Okay, I can buy that. I can buy that.
All right, theory of monoids. Here they are again. This is what, like the third time or something that we're talking about monoids, but it's a different context, which is nice.
Yeah.
Um, all right, the simplest non-trivial example of a Lawver theory describes the structure of monoids. It is a single theory that distills the structure of all possible monoids in the sense that models of this theory span the whole category mon of monoids. We've already seen the universal construction, which showed that every monoid can be obtained from an appropriate free monoid by identifying a subset of morphisms. So a single free monoid already generalizes a whole lot of monoids, but
Stop
there are,
there.
however, okay,
So that's the first question mark when I was reading this chapter, which is if you already have a methodology to create all possible monoids, which is the free monoid, why the heck are we doing all of this?
because a lot of your theories are more general than just monoids.
That's
They're,
true, but I think the next sentence synthesizes it better. The problem is that you may have infinite free monoids. And how you
I'm,
gonna what are you gonna do about that?
well, you make a lot of your theory for monoids.
Exactly, exactly. So like it's such a like I think this should be said. This paragraph should have been said earlier in the chapter, because in the beginning it's kind of weird. Why are we doing all of this? What is the problem that these Lovere theory is solving? And only on 30.3 that we have the answer to that.
Yeah, that's true. That's very true. Um, every monoid must have a unit, so we have to have a special morphism eta that goes from 0 to 1. And notice that there can be no corresponding morphism in F. Um,
No, because this
right,
would be the absurd, right?
yeah, because in F this would be going from voids to units, which is
Yes.
not a thing.
Yes.
Uh, such a morphism will go in the opposite direction from 1 to 0, which in thin set would be a function from the singleton set to the empty set. No such function exists.
Also yes.
Next, consider morphisms from 2 to 1, members of uh, this home set. Well, not a home set technically, I guess. Or is it? You know. Well, they are members of this family of morphisms which must contain the prototypes of all binary operations, which makes sense, right?
Makes
Goes
sense.
from 2 to 1.
Mhm.
When constructing the models, these morphisms will be mapped to functions from the Cartesian product,
Makes
M1 and
sense.
N1 to M1. In other
Makes
words,
sense.
functions of two arguments. And the question is, how many functions of two arguments can one implement using only the monoidal operator? Um, call the two arguments A and B. There is one function that ignores both arguments and returns the monoidal unit. Then there are two projections that return A and B respectively. And then they are followed by functions that return AB, BA, AA, BB, AAB, and so on. In fact, there are as many such functions of two arguments as there are elements in the free monoid with
Yes.
generators A and B.
We've seen this before with the free monoid chapter. That's true.
Um, notice that L mon from 2 to 1 must contain all of those morphisms because one of the models is the free monoid.
Yes. Yes.
In the free monoids, they correspond to distinct functions. Other models may collapse multiple morphisms out to a single function, but not the free monoids. We already knew that, right?
Yeah, we already know this from before.
If we denote the free monoid with n generators n star, we may identify the home set L from 2 to 1 with the home set mon from 1 star to 2 star in mon, the category of monoids. Um, in general, we pick L mon mn to be mon n star m star. In other words, it's the opposite of the category of free monoids.
Yeah, that's a lot of words. I want to break this down because I got very confused with this paragraph. So we start by saying that you're going to use the node monoid with n generators n star. So far, so okay. We may
Okay.
identify the home set L to 1, which is basically all the binary operations
Yes.
in L, with the home set mon 1 2.
1,
So
2, not
my
2, 1.
exactly why the inversion? That's my first question.
Uh, that's a good question, actually. I mean, if truly it is the opposite category of the free monoids, then that makes sense. But that's like
Going from the
what we're
conclusion
trying.
to the premise.
Yeah, that's not good. Not the free monoid. The home set mon from 1 to 2, 1 star to 2 star.
Yeah, this is a home set though. So in the category of monoids, we are grabbing all the morphisms that are going from a singleton element to a tuple.
To a pair of elements, actually.
Yeah, to a pair. A tuple of two. Um,
Not quite. This is with n generators.
so
Hmm.
now we can go past this, but this is one of the questions that I had. Like, how are we getting to this conclusion that okay, actually L mon is the opposite of the category of fermonoids? That's quite a bold statement. So how are we concluding that? We are concluding that from that identification of the home set L21 with the home set mon12. But why that's the case?
Not just 1, 2, but 1 star and 2 star.
Yes.
Uh, hmm. I think this has to do with way back when we were talking about free monoids. Remember when it introduced the idea by using
Universal construction?
uh, yeah, universal construction using base elements to generate more and more elements, right?
Yes. It's an alphabet generation, I believe.
Uh, okay, okay, actually, hmm, hmm. I think I get the generator thing because, like, if you have one generator, that's like, if that one generator, oh, but the generators actually can't be the identity elements, so I don't know.
I think there's also a chance that this is because of the previous sentences in the previous paragraph, because it says, notice that L mon shu 1 must contain all of those morphisms because one of the models is the free monoid. In a free monoid, they
Yes.
correspond to distinct functions. Other models may collapse multiple morphisms in L mon shu 1 down to a single function, but not the free monoid.
Hmm. Right. Uh,
Uh, I don't know, man.
I'll have to go back to this really because, like, yeah, this one paragraph is kind of, I don't know.
Yeah, but anyway, let's fast forward this. Like, it's cool that the category of models in the of our theory for monoids, mod L mon set is equivalent to the category of all monoids.
Yeah,
So
this is pretty nice actually.
yeah, that's well, it's a little weird because the previous sentence before this paragraph establishes that L mon is the opposite of the category of monoid, so we're excluding the monoid, and then grabbing a model from that to set has all monoids now. So like, how can we go from L mon, which just established there's no free monoids in there, and say that the models that go from there
No,
to
no,
set, they are all monoids?
no, no. It's not that there are no free monoids. It's that this category is the opposite of the category of free monoids. That is, it's basically the category of free monoids if you flip all the arrows.
I don't follow. You're saying that if you pick L mon and you flip all the arrows, you're gonna get the free monoid. That's what you're saying.
Yeah,
How can you go from that though to set and have all monoids now? Am I crazy of asking this?
I don't think you are. Like,
Okay,
intuitive.
actually, let I take that back. It's not crazy to say that Elmon is the opposite of the category of Frimonoids because the we know that the Frimonoids is in the version of 2-1, and we're establishing Elmon to be the inverse with 1-2. So, like, it makes sense to be the opposite of the Frimonoids. It makes sense. I just
Yeah.
don't know why, if you make a model of that to set, you get all of them back. That's what I don't know.
Well, it's not if you make a model, it's that the category of models for this particular Lover theory is
The
equivalent to the
category.
category. Yeah.
The category of models. But in all of them, you are going from Elmon, which is the opposite of the Frimonoids. Don't you agree?
Well, yes.
But if you're going, if you don't have a Frimonoid then from the starters, like from the initial category, you don't have one because in
Uh,
order to get one, you have to inverse the arrows of Elmon. Am I wrong? Man,
hmm.
let's go further. Like we can talk about this offline because this is such a uh, like we
Yeah.
already passed 50% and we just had have one question. I think we're gonna get more questions because of the end and the coins, but we're doing great so far. That's fine.
All right. Uh, Lover theories and monads. Of course, monads. As you may remember, algebraic theories can be described using monads, in particular algebras for monads, which is that chapter that we mentioned, I think. Should be no surprise then that there is a connection between Lover theories and monads. Um, let's see how it induces a monad. It does it through an adjunction between a forgetful functor and a free functor.
Let's
This is
stop
something we.
right there.
Okay.
So can we have a 30-second summary of both of these definitions because I already forgot. Forgetful functor and the free functor. I believe the forgetful one is the one that removes the structure
It
or
is,
something like
yes.
that. But what does that mean? Are we going to set?
Uh, not necessarily.
Yeah, so I have to. We should go. We should talk a little bit about it. What does it mean to remove structure? And the free functor. I'm assuming that's the one that goes to set then.
And the free functor.
Oh no, the one that goes to set is the home functor.
Yeah.
Okay, I don't remember what is a free functor. I confess.
Mm, I kind of need to review that as well because I forget about forgetful functors and free functors.
Okay, let's continue then, because I don't. Well, there's definitely some stuff we're gonna miss, like some plot, lore, deductions here, because we're probably gonna explore the properties of these two functors. But let's go further.
Well, the first thing it says is that the forgetful functor u assigns a set to each model. So I guess in this case we're going to set.
That makes
Uh,
sense because set has no structure.
it also makes sense because models go to set. So, well, at least the models we're considering here, right?
Yes,
This is given by evaluating the functor m from mod L to set at the object 1 in
makes
L.
sense.
Another way of deriving u is by exploiting the fact that f-op is the initial object in law. It means that for any law over theory L, there is a unique functor from f-op to it, and this functor induces the opposite functor on models, because models are functors from theories to set.
Wait a moment though.
So, okay.
Uh, the first two sentences, I think I get it. Like another way of deriving u is by exploiting that FOP is the initial backbone. Then
Yes.
we have the functor IL that goes from FOP to L. We already seen this before. But then it says that this functor induces the opposite functor on models. What does that mean?
Uh, it induces the opposite functor on models.
Like taking opposite literally, we're talking from that a functor that goes from L to FOP.
Right.
But that's not what we're doing here. We're going from L to set.
Well, this is a category of models from L to set, or rather, from a particular L to set, I should say. Hmm.
So this is an endo functor.
There's a unique functor.
Yeah, this is IL. We've seen this before. Oh fuck. Internet, Discord. Hello?
Hello.
Okay, so Discord did what it likes to do the most, which is to um, crappy connections.
All right.
Okay, so can you repeat what you
Uh,
said?
no, I was just trying to figure this out as well. This functor induces the opposite functor on models.
Yeah, and here's the thing. This is an endo functor because we are going from the category of models to the category of models. So this is an endo functor.
Not really, because this is not the same category of models.
Oh, okay, so it's a different category of models because one is going from L to set, and the other one is going from FOP to set, which I have no idea why we're doing that, but
F-op is the initial object. There is a unique functor from F-op to L.
IL.
Oh, this is because of contravariance, actually.
I don't follow.
Okay, mod is a category of functors where L is the source, right?
Yes.
Actually, not a category. Well, yes, it is a category of functors because the morphisms are natural transformations. But because this is the source, if you have a unique functor
Fuck. So the
from,
opposite in the text is about variance.
yes,
Jesus. Okay, so this is definitely no risk of confusion.
yes. I mean, there is a we saw like way earlier that there's a relationship between contravariance and opposite categories. Like, I think it was actually back when contravariance was introduced, but it was
But
never really
the
relevant.
author has no freaking right to just say trivially that the functor induces the opposite functor on models and expect us to just, oh, he's definitely talking opposite in terms of variance. Like, come on, man. Like, is that fair?
I mean, it's been a while, so
Well, maybe he thought that, okay, the reader will read this mod L set to mod FOP set, and it's going to immediately click to them that this is definitely the variant functor in comparison to the contravariant one.
a covariant, you mean?
Yeah, the
It's
covariant one in comparison to the contravariant. Sorry.
uh, All right, as we discussed, the category of models is equivalent to set, so we get the forgetful functor. And yeah, you were right, actually. Forgetful functor goes to set, I guess.
Yeah, because there's no structure. Makes sense. Wait a moment though. Are you sure that I'm still bothered by the being mod L set to mod FOP set? I don't think those are categories, Marinho. I think those must be functors, man. Like, am I like, why are you going from one category to the other one in this case?
Because this is a functor on model categories.
Oh, okay,
Like this,
okay.
yeah, this is a category of models from L to set, and this is the category of models from F up to set.
I know what's happening. I'm getting confused between mod and M. M is the functor, but mod is a category of models that have many M's.
Yes.
That's my confusion. Okay.
And more confusingly, the M's inside of those categories are objects, actually, not morphisms.
Yes. Also yes.
Okay, so we got the forgetful functor because we saw earlier that this is equivalent to set.
Yes.
It can be shown that so-defined U always has a left adjoint, the free functor f. This is easily seen for finite sets. The free functor f produces free algebras. A free algebra is a particular model in mod L set that is generated from a finite set of generators, and we can implement it as the representable functor. So, um,
Okay.
given L, we fix N, we take the output as a parameter. That's a functor from L to set.
Mhm.
To show that it's indeed free, all we have to do is to prove that it's a left adjoint to the forgetful functor. So we need to establish this, right?
Wait a moment though. How did M join the party?
This is a variable, basically.
I don't think so. I think M is the functor that we talked about before.
Well, it's any functor, I guess.
Are you sure of that?
Well, it's any functor from L to set, I guess, actually.
From L to set, you said.
Mm,
I don't know. Let's continue. All of these proofs. I'm not here for those proofs anyway. So let's go further.
okay, so we start by simplifying the right-hand side. So this becomes this. We know because we've already seen that this U is determined completely by just M1. And
Mhm.
this becomes this because of exponentials, right?
Mhm. Mhm. Mhm.
And this is the same as this, which we
Yes,
already established.
that's also true.
The adjunction is the result of the Yoneda lemma. So we have this on one side and this on the other. Um, and that's basically it, actually. Together, they define this monad. T equals U after F on set.
Wait.
Uh,
Fuck. F. F is what?
is the free functor.
Oh, the free functor, because F before was the category of the sums.
Yeah, no risk of confusion.
No, yeah, that's fine. Okay, okay, let's go further. Okay.
Mm, so together, the forgetful and the free functor define these monads. So every law of theory generates a monad, basically. And it turns out that the category of algebras for these monads, which is something else that we saw before, is equivalent to the category of models, which
Mhm.
is, this kind of stuff. You may recall that monad algebras define ways to evaluate expressions that are formed using monads. We saw that. Lawver theory defines n-ary operations that can be used to generate expressions, and models provide means to evaluate those expressions.
Wait. So we are basically saying that
Denotational semantics.
yeah. Yeah. So the theory defines the denotational part, and then the what it means, well, how to evaluate those expressions. There are two isomorphic ways of doing, which is monads, algebra for monads, and models.
Yeah,
Okay.
basically.
Okay. Okay.
The connection between monads and Lawver theories doesn't go both ways, though.
That's cool.
Only finitary monads leads to Lawver theories. Finitary monad is based on a finitary functor, and a finitary functor on set is fully determined by its action on finite sets. It's
Okay.
and then its action on an arbitrary set can be evaluated using this coend right here.
Uh-huh.
And I actually had to stare at this quite a bit because I forgot for a moment that this is exists rather than a for all. A for all has the variable on the bottom.
Well, I didn't stare too much on this because I'm still stupid when it comes to coins.
Since the coend generalizes a coproduct or a sum, this formula is a generalization of a power series expansion. Um,
Or we can use the intuition that a functor is a generalized container. In that case, a finitary container of A's can be described as a sum of shapes and contents. Here,
yeah,
Fn is a set of shapes for storing n elements, and the contents is an n tuple of elements, itself an element of a to the power of n. For instance, a list as a functor is finitary with one shape for every arity. A tree has more shapes per arity. Yeah, I don't follow this intuition. Did you get this?
I did actually.
Okay, can you help me?
All right, so uh, think of a list, okay?
Mm-hmm.
A list has basically two parts. It has a structure and it has contents, right? Which are the elements inside of the list.
Yes.
This is basically separating those two parts. So
So
you
you
have a
have
top.
you have a non-ordered and unstructured bucket of data or bucket of content.
It is ordered actually because this is based on this is a product. Remember?
Okay, it is ordered in this case. So you have a sequenced the collection of elements, and then you have the
A
structure in
shape.
which you're gonna put the elements in their respective positions. Follow like intuitively you are picking from the bucket from the order that it's appearing, basically like in a FIFO style.
Yeah, yeah. For a list, this is not very interesting. But if you consider a tree, right? There may be multiple ways to construct a tree of the same size, right?
Yes.
And then you can say, okay, let's follow the convention that this is like, I don't know, we're going to fill in the items in a depth first order or something. And then
Yes.
you
Yep.
just walk
Mhm.
the tree, fill in the elements, and you have the expression, which is tree shaped now.
Damn. So this coend is representing all the possible combinations of contents mixed with different available shapes.
Basically, yeah.
Damn.
Well, not really all. Well, this doesn't exist, remember? So like, okay, for some n, some number n, we have a product of n elements plus a shape of the size n, basically. And the shape
Mhm.
is given by whatever f decides to do with it.
Yeah, this is what the functor is doing. That's crazy though. Okay.
All right, so first off, all monads that are generated from Lawver theories are finitary and they can be expressed as coends. Yeah, this is just replacing f with L of n going to 1.
Mhm.
And conversely, any finitary monad T on set, we can, well, given any finitary T on set, we can construct a Lawver theory. We start by constructing the Kleisli category. We saw this before, right?
Mhm. Mhm.
Restricted to finite sets, this becomes this, where M and N are numbers, right?
Mhm.
Well, numbers representing sets of that size.
Yes.
And the category opposite to this Kleisli category, restricted to finite sets, is the Lawver theory in question. In particular, this home set here, L from n to 1, that describes n-ary operations, is given by this home set, 1 to n.
Oh, so this process that we just described is a way to go from a finitary monad. So if you already have the monad,
And you want
uh,
to go the other way to
yeah, because
Lawver.
before the co-end expression is doing the opposite, right? How if you have the theory, how can you go to the monad? And with
Yeah.
the Kleisli category approach, you're going from the monad to the theory.
Yes. Yes.
Okay. Shit.
Turns out most monads that we encounter in programming are finitary, with the notable exception of the continuation monad, because of course continuations can never be simple.
Uh, sure.
It's possible to extend the notion of Lawver theory beyond finitary operations, but again, we don't actually see this in the book. Uh, and now we're going to explore the coend formula in detail. So here's the formula. We take it over a profunctor P in F defined as this. Um, yeah, that's fine, I guess.
Wait a moment though. I was trying to look again at the Kleisli thing, so I got a little bit distracted. So let's explore the formula. So this is the formula to go from the theory to the monad, right?
Yes, it is.
And then this coend is taking over a profunctor P in F defined as.
This.
N and M are the natural numbers that represent they are the counters of the how many elements.
Yes, yes.
Okay, that's a lot to take in, but okay.
This is contravariant in the first argument. Um, a morphism in fin set is a mapping of finite sets like this, and it describes a selection of m elements from an n element set. Repetitions are allowed. Well, if repetitions are allowed, is it really a set? It can be lifted to this mapping of powers of A, namely A from n to m, so the direction
Man,
is backward.
again, the same shit confusion that I always have. Look at what it's saying on the first paragraph. You have an F going from M to N, and then the description is such a mapping describes a selection of M from N. So like N to M, but that's what my intuition says. But it's contravariant, which means that it is the opposite again. Fuck
Yeah.
me. And the reason its repetitions are allowed, the selection can be a repetition, not the set.
Oh,
The two
right,
sets have different elements, but you can select the different source ones to the same destination ones.
right. Uh, so we lift it and it's backwards, and it simply selects m elements from a tuple of n elements, possibly with repetitions.
Yeah, it's exactly what's happening here on F. Well, no, sorry, not on F.
This one.
Yeah, this one.
For instance, let's take fk from 1 to n, a selection of the kth elements from an n element set. Uh, this is basically like, oh, this would be basically like,
No, no, I take that back. On the image, you don't have repetitions.
on the image we don't have repetitions.
Yeah, we don't have elements on AN going to the same element on AM. Agree?
I think it means that, like, the elements may be equal, but they are in different positions, so they're not really kind of, well, I don't know.
No, but that's just minor detail. Let's continue.
Right, so this function from 1 to n is a selection of the kth element from an n element set. You can think of this as array indexing, I guess.
Mm-hmm.
It lifts to a function that takes an n tuple of elements of A and returns the kth one. So
Yes.
literally indexing.
Literally indexing.
Or let's take f from m to 1, a constant function that maps all m elements to 1. Its lifting is a function that takes a single element of A and duplicates it m times.
Wait.
Uh,
F is doing a collapsing operation, grabbing all the M elements and putting them to units.
yes.
And we are saying that it's lifting to this profunctor is a function that takes a single element of A and duplicates it M times.
Yeah, because it's contravariant, so the lifting is
Ah,
actually from
fuck
1 to
me.
m, you know?
Okay. Every time, every time, I'm gonna die with this problem.
uh, uh, you may notice that it's not immediately obvious that the profunctor in question is covariant in the second argument. The home functor L from m to 1 is actually contravariant in m. However, we are taking the coend not in the category L, but in the category F, which is
Okay,
the...
okay, so this is literally double negation then. Do you follow what I just said?
double negation.
Yeah, because we are going contravariant on L, but L is the opposite of F.
So it's actually covariant in F.
Yes. uh,
Amazing. The coend variable n goes over finite sets or the skeletons of such, and the category L contains the opposite of F, so this morphism from M to N is a member of L from N to M in L. Let's check the functoriality. Uh, we want to lift this F from M to N, so our goal is to implement a function uh, like this. Corresponding to the function f, there is a morphism in L from n to m, which is the opposite direction. And we precompose this with L from m to 1, which gives us L from n to 1.
Jesus, that's a lot of words. Uh, Wait a moment though. I'm trying my best not to follow. So we want to lift a function m to n, and our goal is to implement a function from lm1 to ln1. Corresponding to the function f, there is a morphism in L from n to m because of contravariance. Precomposing these morphisms with lm1 gives us a subset of ln1. Why? How do we know that last part?
Uh, well, because if you take a morphism from n to m, and you give an n to it, it gives you back an m, and you can feed the m to the original morphism from m to 1, which gives you 1.
No, no, no. Yes, but I'm trying to establish the relationship between those three guys to say that the last one is a subset.
Because there may be more morphisms in this home set than just what you can get from here.
So you go from n to m and then from m to 1. That's what you're doing.
Yes, there may be more morphisms that are not possible to obtain by making that stop at m, you know?
Ah, okay. So it's basically like a funnel.
Yeah.
Okay.
Uh,
Ah,
Notice that by lifting a function from 1 to n, we can go from 1 to 1 to n to 1, and we will use this later. So remember this. The product of a contravariant functor an and a covariant functor um, lm to 1 is a profunctor from these two sets
no, but
from Fn.
yes.
Remember that a coend can be defined as a coproduct, a disjoint sum of all the diagonal elements of a profunctor in which some elements are identified, and those correspond to co-edge
Yeah,
conditions. We
I
saw
remember
that,
that much.
yeah. Here the coend starts as the disjoint sum of sets of this form that we just saw over all n's. The identifications can be generated by expressing the coend as a co-equalizer, which is also something we saw earlier, right?
That one I already forgot.
Uh, yeah, remember when you go from like an apex to whatever, I think. Something like that.
Oh, I think it's about that. Yes, 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 yes.
Uh, we start with an off-diagonal term where n and m are different, that's why it's off the diagonal. And to get to the diagonal, we can apply this morphism either to the first or the second component, and the two results are identified. And for some reason, in my copy of the PDF, this variable here is wrong. This should be m, not n.
Yes, in my version, this is correct.
I have shown before that the lifting, but yeah, we saw this before, right? This is so like way earlier.
Yeah, I think this is
From
the profunctor stuff.
yeah, it is. I have shown before that the lifting of f from 1 to n results in these two transformations, this and this. And so starting from here, we can reach both. Um, this one when we lift f on the left, and this one when we lift it on the right.
Yes.
But this does not mean that all elements of an and ln to 1 can be identified with a and l1 to 1, because not all elements of the diagonal can be reached from the diagonal.
Why?
Uh, mm, that's a good question, actually.
Maybe it's just a dumb question because I'm having a hard time following this deduction, but I would like to know why we cannot do that.
Uh, well, if you start from this,
Ah, okay, he
the only
actually answered that after. Remember that we can only lift morphisms from F, which is the dumb backbone. A non-trivial n-ary operation in L cannot be constructed by lifting a morphism
right,
because
because
these are exclusive
I
to L.
yeah, because IL actually introduces additional operations that are not in F.
Okay, so that's why, maybe.
In other words, we can only identify all the addends in the coend formula for which L from n to 1 can be reached from
Yeah.
L11
Okay, so that's
through,
basically
through application of basic morphisms, which are the morphisms from F.
yes. Okay, so that's the reason.
They are all equivalents to A and L from 1 to 1, and basic morphisms, yeah, we just say that. Let's see how this works in the simplest case of the Lawver theory, the F-op itself. In such a theory, every Ln1 can be reached from L11 because, um, well, it's a singleton containing just the identity, and L from n to 1 only has the morphisms from the injections in F.
Which are basic morphisms. Therefore, all the addends in the coproduct are equivalent, and we get
This, which is the identity monad.
okay.
Ah,
Yeah, but have you noticed that? Like, can you scroll up a little bit? Like, something that in this chapter we do a lot. We keep going back and forth between L and F, but L is FOP, which means that we have to keep in mind that there is a relationship between L and F, but we have to reverse. So that's why we go from 1 to n in F and not from n to 1.
yeah.
Like, okay, that's too much brain work, man.
Lawver theory of side effects. Uh,
This is the last section, by the way.
this is the last section. There's no 30.8.
Yeah, that's challenges.
That's challenges. All right. Since there is such a strong connection between monads and Lover theories, it's natural to ask if Lover theories could be used in programming as an alternative to monads. The major problem is with monads is that they don't compose nicely. There's no generic recipe for building monad transformers.
That's true.
That is very true, and also apparently very annoying. I don't really know myself because I'm not a Haskell programmer most of
Yeah,
the
yeah,
time.
but it is annoying because, well, I can tell you later why it's annoying, but it's such a dummy problem. It's so dumb that Lean already fixed it, so it's fine.
Lover theories have an advantage in this area. They can be composed using coproducts and tensor products. On the other hand, only finitary monads can be easily converted to Lover theories. The outlier here is the continuation monad, and there's ongoing research in this area. See the bibliography.
Mm-hmm.
To give you a taste of how a Lover theory can be used to describe side effects, I'll discuss the simple case of exceptions that are traditionally implemented using the maybe monad. So it's generated by the Lover theory with a single nullary operation from 0 to 1.
Wait, but haven't we already established that this morphism can't be done?
In the L category, it can because 0 is the unit there.
I don't follow.
Because the Lover theory is based on F op, not F.
Yes, but haven't we already discussed that if you have a function that goes from void to a, you cannot call this function ever?
That is true, yes. But
So
the
like,
thing is that 0 is not void in L. It is void in F, but not in L.
no, 0 in L is what? Unit?
It's the unit, yes.
And 1 is what?
It's whatever
Value of the
variable you have.
maybe set is available then.
It's whatever variable from your algebra, whatever sort you have there.
Okay, a model of this theory is a function that maps 1 to some set A that and maps the nullary operation to a function.
Which is this function. And we can recover the maybe monad using the coend formula. Let's consider what the addition of the nullary operation does to the home sets, well, from n to 1. Other than creating a new L from 0 to 1, which is absent from FOP, it also adds new morphisms to L and 1. They are the
Yes.
results of composing morphisms of this type with our new 0 to 1.
Mm-hmm.
They are all identified with this in the coend formula because they can be obtained from this type by lifting 0 to n in two different ways.
Yeah, this is the perfunctor stuff.
And in this one, the variable is correct. Amazing.
Yes.
Yeah, so we can lift f on the left and on the right, and then we can um, say they are the same, and it reduces to this, or using Haskell notation, this,
No, which is true.
which is equivalent to the usual definition of maybe.
Yeah, and then notice that the theory only supports raising of the exceptions, not their handling. Uh,
Yeah, you can fail, but you can't really do anything with it.
you can't catch it if you fail.
Yeah.
Okay, so before I end the recording, any more comments or considerations?
This chapter is very dense. It's pretty interesting, and I don't fully get it.
I will say the same, but I want to discuss back to the 0 thing to finish. So can you repeat again why the 0 to 1 works in L and doesn't work on F?
If you go back all the way to where's the diagram? Here,
Mm-hmm.
right? In F, 0 is the initial object. It's basically void, right?
Yes.
Because we're talking about sums and the unit for the sum tensor type, which is void. So, but L is not based on F directly, it's based on the opposite of F. If you flip all the arrows, then this becomes the terminal object, which actually corresponds to unit. These all become products, and the tensor unit for the product in this case is the unit type 1, not void.
Wait a moment though. I don't think I'm having some confusion because I remember that IL introduces new operations, right? And if you look
It
on the
does.
L diagram, there is an arrow going from 0 to 1.
Yeah, like in this case, you could say, okay, ignore these arrows from 2 to 1. The maybe, the Lawlor theory for maybe basically introduces this arrow, which does not exist here, you see?
Yeah, but I didn't quite get it what you said before. So when you inverse the arrows from F to FOP, 0 is not void anymore. 0 is unit because now 0 is the terminal object.
Yes, it's not the initial object anymore because we flipped everything.
Ah, okay, so the interpretation of 0 changed because we reversed the arrows.
Yes.
Ah, my god. Okay. I'm gonna finish the recording now. Any more comments?
Bye, future people.
Bye.